a bit more on functions. Obviously, this topic is called functions and graphs. And we're going to talk a bit more about what a function is. So a function, the top part here, the graph of a function consists of the ordered pairs, so meaning when you have your coordinates x, y, that's called an ordered pair, plotted on a pair of axes, where the x and y values, where x and y values are the input and output variables. So where you sub in x values and you get out the y values. Just like when you sub in those little table of values, when you did them to sketch straight lines, you choose your x values, you sub them in to get the y values, okay? No 2 points on the graph have the same x coordinate. Yes, I'm recording. Thank you. No 2 points have the same x coordinate. Now that is the definition of a function. Another way to say this is that the function is a set of ordered pairs in which no 2 ordered pairs have the same x coordinate. And we learn to test for a function. Do you remember what it is? No. The vertical line test. That will tell you when you do that vertical line whether if you have an x value, whether you've got 2 y values or not. So if you have 2 y values for that x value, then it's not a function. So that's why we have that vertical line test. Okay? A function should only have, for the x value, it should only have one possible y value that you can get. Okay? In most graphs in this course, the points they join up to make a smooth curve, like your straight line, like your basic parabola, like your exponential even. They are all functions. However, it does say the word most because there are some graphs that will have a broken section which we call discontinuous, a discontinuous point. And they can still be functions as long as there is only one y value for every x value. And I'm going to show you one of those in the examples, okay? Domain and range, you know these from last year as well. I'm going to be asking you to find the domain and range of some graphs. The domain means that I'm asking you what are all the possible x values that that graph can have. And if I ask you for the range, this is why we have class last period, so he can escape early. That's why. Yeah. Anyway.
It's great.
Okay, so the range is the possible y values. Okay, so domain means possible x values, range is possible y values. Another word you need to know is the word natural domain, another term. A natural domain occurs when there are no restrictions given, and the domain is all x values that can validly be substituted into the equation. What that means is, if I were to give you the equation of some kind of graph, let's go with this one, y is equal to x squared, okay? That naturally has a certain domain, and it's actually all values of x. I can sub any value of x that I want into that. The opposite of a natural domain is what I would do. If I think of it as a man-made domain, I can enforce my own domain on that. And I could say I could restrict that to be x between, say, -2 and 2. As soon as I restrict it, it is no longer a natural domain because I have restricted it, okay? So that's an example of an unnatural domain. All right, so we're learning about functions where every x value only has one y value. We then have this term relation. Now, a relation is any set of ordered pairs. Like a function, it has a graph. Like a function, it can have a domain and range. Unlike a function, though, this is the difference, a relation may have 2 or more points with the same x value. Okay? So, for example, a circle, plotting a circle, it's not a function. Okay, I draw my vertical line through that, and it cuts through twice. For that x value, if I draw it through one, it's cutting that circle in 2 places, so it's not a function. But it is a relation. Anything that I can give you an equation for, Any graph that I can give you an equation for where there's a relationship between x and y, that's why it's called a relation. That's why it's a relation. There's a relationship between x and y. Whereas a function is much more specific, it will only have one y value for every x value. Yeah? So that means that a function is a special type of relation. Relations basically cover all the different graphs that we have, and the functions are the more specific ones that only have the one y for every x. Okay? It's like a little subgroup. Relations that pass the vertical line test, so that's mentioning our test for us, a reminder. If our relation passes the vertical line test, then it is a function. Functions include what we call one-to-one relationships or relations. Now, an example of a one-to-one relation would be a straight line, where for every x value that I have, I've only got one y value that I get from that. So I sub in x is 1 and I get y is 2. Yeah, x is 2, y is 4. There's only one x gives me one different y value each time. Then there's this other one here that says many to one. It is also a function, and an example of a many to one function is our parabola. Okay? I could choose x is equal to 1 or x is equal to minus 1 into my basic y is x squared parabola, and both of them would give me the answer for a y value of a 1 up here. Yeah, so that's in y equals x squared. If I had 1 squared, I get 1. Negative 1 squared also gives me 1. So that's many or multiple x values that give me the same y value. That's what we call a many-to-one relationship. Both of those types of graphs are types of functions, but you'll be hearing those words, one-to-one and many-to-one, and that's what it means. Mapping, some more terminology that we need. Functions, but not relations in general, are also called maps or mapping. The word map may also be used as a verb. So, for example, if I have a function, f of x equals 2 to the power of x, I'm reading from the document here. If I sub in that x is equal to 3, okay, 2 to the power of 3 is 8, correct? So subbing in that x value of 3, I get 8. But we can use the word mapping to describe that. We say that 3 is mapped to 8. So subbing in the 3, we get the 8. That's how that terminology is used. Or in reverse, that 8 is mapped from 3. Get rid of that word 2 because that just doesn't make sense. Okay, 8 is mapped from the 3 because it's from the 3 that we get the 8, right? So that's how that word mapping is used. Here are our examples. Number 1, apply the vertical line test to give the correct label for the following relations. State the domain and range of each graph. Okay, so first of all, we're doing our vertical line test, and you can draw imaginary lines anywhere you like. If I can draw a vertical line through it, that's my phone.
Is it bracket?
Is it? It totally is. Who's calling me? That was totally a telemarketer. Anyway. I know it's normally next door, but Muhammad's doing his testing there, so I didn't want to leave my phone in there. Back to this. If I can draw the vertical line and it only touches once, then it is a function. If at any point I can draw it and it cuts twice, then it's not a function. Okay, so this one is a function because it's only ever going to cut through once. But there was a second part to this question. I also need to say what the domain and range is. So the word domain, do you remember what that's talking about? Domain is talking about all the possible x values. So when I look at that graph, what x values can I use? Or really what you're trying to think, is there any that I can't use? Is there any x values that I can't sub in to get a y value? No. I mean, I could make the graph even bigger and go further out that way or further this way. I can sub any x value in I want. So for straight lines, they're always, unless they're vertical, that's a catch. But for sloping straight lines, they are always all real x. for domain. What about the y values? Is there any y values that I cannot have? No. So again, for a straight line, sloping straight line, it's going to be all real y values as well. Okay, so that straight lines hopefully are the easy ones. All real x and all real y. Moving on to a parabola, but this is a sideways parabola. Our vertical line, let's draw it over here. If I draw it there, straight away I've cut it in two places, which means that it is not a function. Not a function. Okay? But we can still do domain and range even though it's not a function. So domain are the possible x values. Is there any x values that I cannot have?
Anything less than negative 3.
Yeah, so this point here where the parabola turns around, I'm never going to be able to get x as -4, -6. My graph doesn't exist down here for these x values. This point here is the critical spot where the parabola kind of ends in terms of x values. So x must be greater than or equal to -3. Okay, so x is greater than or equal to -3 is my domain. All right, the range, the possible y values. Leave it off. Is there any restriction on what y values I can have? No, okay, my y value is going up slowly, but it is going to keep going up as far as I want it to go, and it is very slowly going to go as far down here as I want it to go. Okay, so I've got all real y values. Okay, next one, a circle. Vertical line test. Draw it on there. If I draw that, there's lots of places I could draw that, it's going to cut through twice, meaning that it is not a function. Okay, looking at the domain, the x values. So you're looking on my x-axis. We've got these points here where my circle, that's the edges of my circle, right? My x values are never going to be outside of that circle. It only exists between that number, which is -5, and that number, which is a +5. So to write that, you put your x in the middle. When it's between two values, you always use less than signs, less than or equal to, which means that it's between -5, so that's saying x is greater than -5, and it is less than 5. Or x is between -5 and 5. What about the y values? Yep, same deal. It's going to be between -5 and 5 again, because it's a circle for the y values. And part D, vertical line test. Can I draw that anywhere and have it touch more than once? No. Okay, so it is going to pass the vertical line test, making it a function. Okay, domain of that function, the x values. Is there any x values that I can't have?
Yes.
Which ones?
No.
No, there is no x values that I can't have, so it's all real x. I could keep getting, I know my graph doesn't show me these ones yet because it gets way too steep, but I could come out here and then my parabola would just be way up here somewhere. You have to assume that the graph is just going to keep going. It's not just going to stop there. It will keep going. What about the y values? We have this turning point, that's right, which means that my parabola is never going to exist below -4. So that means my y value must be greater than or equal to the -4. Good. All right. So we can identify functions and we can find domains and ranges from a graph. How about if we don't have a graph? Question 2 says find the natural domain, which means we're not putting any restrictions on it, just this graph in its natural habitat. What would the domain be? Okay, now, like we kind of were hinting at in the other ones, is there any values that it can't be, is what you're looking for? Is there something that it can't be?
0.
And when you have a fraction in your equation, you have to always think my denominator cannot be 0. Okay, you can never divide something by 0. It's one of our mathematical rules. You cannot divide by 0. So any x value that makes that 0 is...
So it can't be 1.
That's right. So x cannot be equal to 1. Any other x value I can have. That's the one that I can't have because I can't divide by 0. So any fraction type question, you'll be doing that kind of thing. Square root signs, Ben.
What would that graph look like?
That is a hyperbola moved sideways and you'll have a vertical asymptote at 1. They're the ones that look like...
I mean, how's it a hyperbola?
Oh, that's -1, sorry. Positive 1. It's like that. Okay, the next one with square root signs. Square root signs. You can't... What can't we do to square root signs? With Ashton?
Negative. Can't be negative.
That's right. You can't square root a negative number. So, as soon as you see the square root sign in your equation, whatever is underneath it, the 3 plus x, must be greater than or equal to 0. It can equal 0, it just can't be less than it, okay? And if I solve that, which means I subtract the 3 across to the other side, that means that x must be greater than or equal to -3. Okay, so they're the two types, really, that you're going to have. The fraction, where you're looking out for that denominator, and the square root, where whatever's underneath has to be larger than or equal to 0. What's the matter?
Can it be -4? No. Because that makes it 0. 3 minus 3.
It can, 3 minus 3 is 0, and the square root of 0 is still 0. It just can't be negative. 0 is okay, but it can't be negative. So I can't put in -4, like you said, because 3 minus 4 is -1. Okay, square root of -1. Calculator says, big error, can't do it, doesn't exist. Unless we do imaginary numbers. We don't do imaginary numbers.
Like this, in extension, do we do stuff with
E, yes, you'll do that in advanced.
and an I?
And I is only for extension 2, which is the square root of -1. So on the door here, where it's got square root of -1, that means I.
How?
So we use it so that we can do calculations with square roots of negative numbers.
Could Mr. Ralph come in and give us a seminar
Wait,
on
so,
that?
not so, miss.
Can you read? Let's not get distracted. Look, okay.
So, miss, with
All right.
2B,
Yep.
could you do something with I?
We're only looking at the natural domain, okay? We're not going to overcomplicate this, so no. No. Overcomplicating, way overcomplicating. Lachlan?
I don't get what the natural domain is.
So natural domain, I talked about at the beginning of the lesson. Max? The natural domain is just if the graph, if I give you the equation of the graph, and what are the possible restrictions on that, normally. So like a parabola, what are the possible x values and what are the possible y values that I can have, domain and range. The thing that is not a natural domain is if I put a restriction on it. So I say, I want to sketch that parabola between -2 and 2. I have put a restriction on it that has given me a limited domain.
So it's a natural domain.
So it's just saying
equals
for every part of x value, what possible x values can I have for all the possibilities?
So it's always natural unless it's like...
Unless, that's right, correct.
I'm going to write it.
All right, question 3. We looked at this a little bit last lesson. We have a function here that has 2 different equations. We have 2x plus 3 when it's greater than or equal to 2, and minus 2x squared if we're less than 2. So first of all, A is what we did last lesson, where we want to create a table of values between -1 and 5. I am going to be a little bit sneaky here. So there's my x values, there's my y values. Because I'm going to have to sketch this graph, I'm actually going to find out what is happening at 2 for both of them, and you'll see why. So when I draw my table, I'm going to go -1, 0, 1, 2. I'm going to repeat the 2 for when it changes graph. 3, 4, 5. It will all make sense when you see what this graph looks like, okay? All right, at negative 1, we're in the less than 2 category, right? Negative 1 is less than 2, which means I want to sub negative 1 into that equation. So negative 1 squared is 1, times by negative 2 is negative 2. Okay, 0, still in this category. So 0 squared times minus 2 is 0. Okay, we keep going. 0 is still, 1, sorry, is still in this category. 1 squared times minus 2 is minus 2. Now 2 is technically in that category, but I want to see this graph would go all the way to 1.99999. It needs to go all the way to the 2, but just not right at it. Okay, so that's why I need to find out where that's going to be. So if I sub 2 into here, 2 squared is 4, times the minus 2 is minus 8. All right. However, we know that at 2, we should be using this graph here. We should be using this one. So we sub 2 into this one. 2 times 2 is 4, plus 3 makes 7. See how those are 2 different values? That's because it's a discontinuous point on my graph. Okay? 3, subbing 3 into here. 2 times 3 is 6, plus 3 is 9. 4 into here. 2 times 4 is 8, plus 3 is 11, and subbing 5 into the same one, we get 13. Okay. To draw this, hopefully you have a ruler that you can be using. No? No rulers? All right, my x values go from negative 1, 0, 1, 2, 3, 4, 5. So you'd measure centimetre spaces for each of those. My y values go all the way up to 13. Maybe you'd have to go counting by 2s to fit that in. So 2, 4, 6, 8, 10, 12, 14. And we need to go down to negative 8. 2, 4, 6, 8. Okay. So this graph, we have, when we're less than 2, we're drawing minus 2x squared, which is a parabola, isn't it? Okay, so let's plot the first 4 points. We have minus 1, minus 2, which is here. Then we have 0, 0, 1, minus 2, and 2, this naughty point that I included, okay, it's not, remember I said it's not actually at that point. Everything up to that point, 1.999, as many decimal places on that as you want, right up close to it, but it will never actually be exactly at that point. What we do is we put an open circle there, okay? So at 2, negative 8, we put an open circle there saying, I know it's coming right up close to that point, but it's never actually going to hit it. Okay, does that make sense? So I draw my parabola. It comes up from there, it goes to the origin, and I can put an arrow on that left-hand side because it would keep going. Okay, it would keep going this way, but it ends there. Once it ends at this point, then it changes and it becomes this second equation, 2x plus 3, that's a straight line. It's now going to become a straight line. So let's plot from here. 2, 7 would be about there. 3, 9, 4, 11, and 5, 13. Now, that first point there is a solid point because that was the equal to. Remember when you did inequalities, if you had an equal to sign on it, you coloured it in, and if it had just the less than or the greater than sign, you did the open circle. That's exactly what's happening here. This one had the less than sign on it, so I did an open circle. This one is going to be a big coloured in dot, and then my line is going to be coming up, a bit more accurate than that, through there. And that is a function. Because even though I have that discontinuous point here, if I draw a vertical line through it, and that's probably the point where you want to test, even drawing a vertical line through that, the graph does not exist right there. That's an open point. So it is only going through once. Okay, it is a function. No, a bit of a technicality. So that was an example of when not all functions are smooth graphs. We can get a few that look a bit like this. Now this question here is like question 15, your very last question. Okay, this is the harder type of question that you're going to have to do.
Wait, was that
Yeah.
question?
No, so your question 15 here, it's like that one there.
Oh,
So the last thing we have to do is it says what happens at x equals 2, that point there, that very special point. We identify that there is a break there. Okay, so there is a break in the graph at this point. Oop, spell break. Okay? Yeah, I do know, thank you. Okay, what does that mean? It means that the graph is not continuous. So the graph is not continuous. Okay? Because it had a break. And that's it. Fantastic.